we're going to be taking a look at standard T1 today. Standard T1 is a pretty essential standard for trig and for calculus because it deals with degrees and radians and finding the values of the trig functions at those. So trig functions come into play whenever you have a situation that repeats itself or is periodic. Then to find the y values, the x's are always degrees or radians. And so we have to be able to evaluate. Now, we have to be able to evaluate with or without a calculator. With a calculator, it's pretty straightforward because you just punch it into your calculator. Without, it's a little more tricky, but we have a couple of tricks up our sleeve that make it a little bit easier. All right, so the standard is twofold. It's one of the more important standards. We connect degrees, which come from more triangles and shapes, and radians, which are circular functions, together in a picture, which we then build off of so that we can solve problems and find particular values. Okay, so this is what we would call the unit circle. And I know we've kind of already talked about this, so it's good for us to review it. So you have to imagine that this is the y-axis, this is the x-axis. Okay? And maybe even label that x and y. All right. I want you to draw a right triangle in to represent an angle that's opening up. Now we're just going to deal with one triangle, but technically we call this a reference triangle, but this reference triangle could be anywhere. You could draw it over here, you could draw it down here, or over here, and all the same things that we're going to talk about apply. Okay. All right, so we're going to consider, like if this is a ray, like so it's a terminating side of an angle, and if it keeps opening, then the point here is going to trace the outside of the circle. Because we know any point on the outside of the circle is the same distance away from the center. So we're going to actually label that as R. We can label this as theta. And then this is some kind of x value because it's a horizontal, it's part of the horizontal axis, and this is some sort of y value. But those x's and those y's would change depending on, like even if we move this point a little bit, or the angle opened a little bit more, the x and y values would change. Okay. So make sure I'm not missing something here. Yeah. Okay. In the unit circle, the equation for the unit circle is x squared plus y squared equals r squared. And r is always 1 unit. Now technically, if we expanded this from not just the unit circle, but bigger to maybe be 3 units long, the same situation would still apply. Just your radius would be more. So whatever your radius is, that is considered 1 unit. Okay. I think we're going to come back to this section here. Okay. I think I'm going to have you flip this, and we'll just kind of write this way. Right. The connection between triangle and circular trigonometry starts with this picture. Technically, the circle is formed as the ray, which is the hypotenuse of the triangle, rotates around the origin. So, because of this connection, properties that previously applied only to triangles will now also apply to circular functions. And when I say circular functions, I'm talking about functions that repeat, not necessarily they aren't necessarily a shape, but they just repeat the process over and over. Okay. Go ahead and flip. We'll probably flip that beginning page again at some point. The 6 trig functions. You have sine, cosine, tangent. Their abbreviations are sin, cos, tan. These are the 3 most common. The other 3 are cosecant, secant, and cotangent. Abbreviations CSC, CEC, and COT. Okay. Now, you have 6 trig functions, and these 6 trig functions, the values of them are ratios. And in triangle trig, what you've done before, they're ratios in a right triangle. But when you graduate from just looking at a shape to looking at functions that repeat over and over again, you can't be married to always looking at this shape. We're only looking at sine, cosine, and tangent as side lengths. Technically, they always are, because anything that repeats would fit some type of cyclical pattern. But the original values, or the original way we look at sine, cosine, tangent, and these 3 are comparing or setting up ratios in a right triangle. Okay. All of these boxes, by the way, should be thetas. So I'm going to fix that really quick. And then before we actually write the values for each of these, whoops, sorry, these should be actually x's. Okay. We're going to draw a picture here in the middle. And really it'll just look like the first quadrant on the front page that we did already. Okay, so you have this ray. We're going to label it R. We have this as Y, and this is X. The other way that you can see this, if this is my theta, this is my adjacent side, or the side of the triangle that's closest to this. This is my opposite side for my angle, and this is my hypotenuse. Okay. Now the X and the Y and the R come into play when you're looking at a function or cyclical function, because then it's placing that function on the coordinate plane. So you have X and Y and R. Because technically you can't use adjacent, opposite, and hypotenuse for those types of problems, because you're not necessarily always dealing with a triangle shape for those problems. Alright, so the definition of sine, or how you find the value of sine, is you need to look at the right triangle, and the value or the ratio for sine is sine of theta is opposite over hypotenuse. Cosine's definition is adjacent over hypotenuse. Tangent is opposite over adjacent. Cotangent, secant, and cosecant are the reciprocals. So not completely opposites because you don't make them negative, but you do have to flip the fraction. So cotangent is adjacent over opposite. Secant is hypotenuse over adjacent, and cosecant is the reciprocal of sine. So it's hypotenuse over opposite. Then when you're talking about sine of x, cosine of x, tangent of x, these are called coordinate form because you're no longer just looking at the shape. You're looking at it in terms of x and y and r. Same type of deal. Sine of x, if that's my theta, or my angle, is going to be opposite over hypotenuse. Cosine is going to be adjacent over hypotenuse. Tangent is going to be opposite over adjacent, or y over x. Cotangent, you flip tangent. Secant, you flip cosine. And cosecant, you flip sine. Okay, so these are all the definitions of the trig functions, or this is how they're defined. Okay, so how do we find the sine and cosine of any angle given the coordinates? Oh, you know what? Something I forgot to add. Go back to your unit circle. No, never mind. Actually. Okay. So, how to find sine and cosine of any angle given the coordinates? Now, I'm going to write down the steps, and then we'll actually do an example. You're going to plot your point. And draw your reference angle. Actually, let's make that your reference triangle. That'll make more sense. So plot point, draw your reference triangle. Next thing you need to do is label each side of your triangle. Use the ratios to find trig values. If you've ever heard of SOHCAHTOA, that's how we remember what goes with what. So like sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So that's a little phrase there to at least help you if you're not quite sure quite yet what the order is. Okay, we're going to do an example together here. Alright, if I gave you a point, let me try to find a problem. Here we go. Okay. The terminal side of theta contains the point 4, -2. We're going to sketch our theta and find sine of theta and cosine of theta. Alright, so first thing we're going to do is actually plot the point. So 4, 1, 2, 3, 4, -2. There we go. We draw a reference triangle, which will look like this, and then we label each side. So I know that this length here is my x, that's 4. This side here is my y, which was -2. Then to find my r, I'm going to use the Pythagorean theorem. So -2 squared plus 4 squared equals r squared. So this is 4 plus 16, so 20 equals r squared, or r equals the square root of 20. Okay. And then to find the values for sine of theta and cosine of theta, now that we have, there's my theta. Now that we have the triangle, I have all the values I need to find sine and cosine. If you remember back here, sine is the opposite side from the angle over hypotenuse. So sine will be opposite, -2, over hypotenuse, square root of 20. Cosine is adjacent over hypotenuse. Now, usually your answers aren't written like this. They like to rationalize, so we're going to multiply this by a fancy form of 1. What that does is gives me 2 square root of 20 on the top, and and just 20 on the bottom. I could reduce that one more time, so square root of 20 over 10. And same thing here. That would end up being 4 times the square root of 20 over 20, and you could reduce and get square root of 20 over 5. Okay. Do the same thing here. Terminal side of theta contains the point -3, -5. Sketch and find cosecant of theta and tangent of theta. Okay, so we're going to plot these points again. 1, 2, 3, 1, 2, 3, 4, 5. Draw your reference triangle. Here's your theta. I know this side value is -3, this side value is -5. And then your hypotenuse here would end up being 9 plus 25, which is 34. So r is the square root of 34. Okay, cosecant and tangent. Cosecant is the reciprocal of sine. So if sine is opposite over adjacent, if sine is opposite over hypotenuse, then cosecant's the reciprocal of that. So it'll be hypotenuse, so square root of 34 over your opposite side. And then tangent is going to be opposite over adjacent. And that's what you would have. Notice we don't need to find theta yet. It's not what the question is asking you. It's asking you to find the value of a function. So we found the value of both functions. Alright, for the last 3 problems, we're going to be using these special triangles. These special triangles are 2 scenarios that pop up a lot of times. And when you have these special scenarios pop up, the ratios, the sides, or your sine, cosine, tangent values will always be the same. The first one's a 45, 45, 90. The ratios are 1, 1 to square root of 2. The other one is 30, 60, 90. The ratios there are always 1, square root of 3, and 2 is your hypotenuse. So it doesn't matter how long the sides are. Like if this side was 10, then that would automatically make this hypotenuse 20 if we knew the angles were 30, 60, and 90. So it's just showing you how to set it up. Okay. We're going to do 2 together, and then we'll probably do the last one as a warm-up in class tomorrow. Alright, so we're going to find the exact values. Now, let's start with an easy-ish one. Exact values mean no decimals. So we're going to find the exact values of 300. Okay. 300 degrees. First thing I'm going to do is sketch it. 300 degrees is in the 4th quadrant. Oh, you know what we didn't do? unit circle. In this section here, all x values are positive, all y values are positive. So we have plus, plus. In this quadrant here, x values are negative, y values are positive. In this quadrant down here, x values are negative, y values are negative. In this quadrant, x values are positive, y values are negative. That's going to make a difference. We start looking at some of these ratios. It makes a difference what quadrant you're in. For example, you know what, actually I think I'll end with example 3. So we sketched 300, and that's just to determine what quadrant it's in. It's in quadrant 4. In quadrant 4, your x values are positive, your y values are negative. So if I'm finding sine of 300 degrees, cosine of 300 degrees, tangent of 300 degrees, and then vice versa, cosecant 300, secant of 300, and cotangent of 300. Oh, you know what? I missed a point of exclamation here. 300. Let's go back to my two triangles. To find exact values, it has to fit one of these two triangles. However, you don't see in either one of these triangles the angle of 300. You will never see an angle of 300 in a triangle, because then it wouldn't be a triangle. So remember in the first section when we talked about reference angles. Reference angles are how we actually find the values for all these. So the reference angle here, or the space between the x-axis and where the angle ends, is 60 degrees. Okay, so we look at the 60-degree angle. We're going to find all the values for sine, cosine, tangent based on this 60-degree angle. Sine of 60 degrees is opposite over hypotenuse. So that first problem there should be square root of 3 over 2. You know what? I'm going to draw the reference triangle right here. 30, 60, 90. 1 square root of 3 to 2. Okay, so we're at 60 degrees. Cosine of 300, but we have to use 60 degrees as the reference angle because this angle and a reference angle get you the same value. So 60 degrees is adjacent over hypotenuse, so it's 1 over 2. Tangent is opposite over adjacent, so square root of 3. Cosecant is the flip of this. And if we rationalize, we get that value. Secant is the reciprocal of cosine, so I'm just going to flip 1/2 to get 2. And then cotangent is the reciprocal of tangent, so you'd have 1 over square root of 3. But if you rationalize it, it'd be square root of 3 over 3. So these are all the correct quantities, or correct values. But because my angle that I'm looking at, 300, is in the 4th quadrant, that means that anything that has an x, or in this case, what we would call the excuse me, what we would call the opposite side, is going to be negative. So that happens with sine, tangent, cosecant, and cotangent. Now, the way to remember what function is positive and what function is negative in each quadrant, we use this phrase, all students take calculus. So all the functions are positive in the 1st quadrant, sine is positive in the 2nd quadrant, tangent is positive in the 3rd, cosine is positive in the 4th. That's because cosine has nothing to do with the opposite side. So see, cosine's positive, everything else is negative. And then we'll pick up with that for example 4 and example 5. We're done for today.